Now for this session's last presenter, that will be Carlos Ramos from Polytechnic of Porto, Portugal. And he will be presenting the paper Machine Learning Applied to Industrial Machines for an Efficient Maintenance Strategy, a Predictive Maintenance Approach.
Thank you very much. Good afternoon. I will present a work related with the application of machine learning techniques to industrial machines for a problem related with the maintenance, namely the predictive maintenance. My background is in artificial intelligence, not in power and energy systems, but I have worked during many years in problems related with manufacturing, and usually in problems related with planning and scheduling of manufacturing systems. This means we have a set of orders that we have to schedule in manufacturing cells or manufacturing lines, and we considered temporal reasoning, namely due to the due dates of these orders. So we need to decide the sequence in which the products or the components will be manufactured, and things like failures in accomplishing deadlines, or like problems with excessive setup times in the manufacturing lines are to avoid. But on the last years, we have observed that these manufacturing systems, the question of energy is more and more important due to the costs of energy. Now the problem is not just a question in terms of time to decide where the manufacturing orders will finish to avoid deadlines, is also to decide in which part of time we will do the manufacturing, trying to take advantage of some intervals of time in which energy costs are lower. This work is not related with this, is related with a different aspect, that is the question of maintenance, namely because when we have a problem in the machine, it's problematic because this machine will not work anymore, so I will fail in accomplishing the deadlines at all. My clients will not be satisfied about that, but at the same time, when the machines they don't broke from one moment to another, usually they have we can obtain information about the machines with sensors, and this means that we can know sometime before that maybe the machine will not operate well in the near future. So the question is to decide when we will do some maintenance in the machine. We have an introduction, then we'll speak a little bit about the data set, the training and testing, the proposed methodology, and the results and discussion and conclusions. So as I referred, there has been a shift in traditional industrial maintenance strategy to systems that are able to forecasting the machine lifespan, and this is very important because if I have some forecasting, I will be able to decide in which moments it will be better to do the maintenance of the machine with less impact to the industrial system. The machine health has a significant impact in the machine energy efficiency questions, since if the machine is not working well, maybe we'll be doing lots of work that will not have the quality, the necessary quality, and sometimes even we needing more energy, and sending some products and components are not suitable to go to the clients. So predictive maintenance can improve the machine health. This means to try to solve the problem previously, to have an idea of what will happen next in the system. This work is associated to an international project, MOVE project, that has finished this year. For the dataset, we are using a synthetic dataset with 10,000 data points, in which more than 300 represent failure situations, and more than 9,600 represent no failures. So we have a ratio of 1 failure by each 28 no failures. It is available in EI machine learning repository for predictive maintenance dataset. The dataset considers the following features that are here: the air temperature, the process temperature, the tool rotating speed, the tool torque, the tool wear. That is something related with a gradual failure of the cutting tools. This means that the tool starts to fail gradually due to the use, and the machine failure stats with a binary values, 0 for non-failure and 1 for failure. The methods that we are using are artificial neural networks and the random forest are the two methods that we consider in this approach. The methodology uses the most recent machine data from the machine databases in our industrial facility. So as we have in the figure, we have the machine database. We provide the data acquisition. We have an important effort in data pre-processing. We will refer in one of the next slides, and then we will train the machine, train our machine learning models, and then we'll be able to use the model that we have obtained. The data processing, basically we have 6 points that are necessary. The first is the data aggregator. Will combine all acquired data in a single data file. Then it's important to do some normalization. This means to have standard data units and types, and most of the times this is a critical problem in data that we have. The third point is data imputation. Filling with miss values. It's quite normal when we use data sets, we have some missing values, but it's important to consider possible values for these missing values. Then the fourth step is the data filtering, removing some potential incorrect or irrelevant data. This is quite normal in data processing as well. And then the data engineering to create or remove features to better adapt to the problem in hand. And the data balancing machine data between failure and non-failure points, because otherwise our model will not be good for our purposes. The preprocessed data is using to train our machine learning models using neural networks on one hand, and the random forest, that is a well-known method based on decision trees. And for real-time application, we'll use we'll use our models for the prediction. That is our purpose. The artificial neural network and the random forest models are trained using keras for the case of artificial neural networks, and scikit-learn for the random forest as well. and we use an automatic hyperparameter optimizer. So as you can see here, it's difficult to read, but for hyperparameters like the batch size, like the epochs, like the neuroactivation function, and so on, we have different possible values, and we obtain the optimal value or optimal parameter to apply. For example, for the neuroactivation function, ReLU was what has given for us the better result. For example, for the hidden layers, we are considering here 4 layers. It's important to decide the number of neurons in each layer. It has been obtained 25 for the first, 20 for the second, 15 for the third and the fourth as well. This is the thing, the kind of things that is done for the artificial neural networks, and the same kind of things of hyperparameters considered for the random forest. In this study, the random forest has demonstrated to have better performance. You can see here, basically what we have here is the traditional evaluation using true or false positives and negatives. In this case, we have the failures and non-failures. In the case of non-failures, we have a small difference between them. In the case of non-failure, we have a considerable difference. In the case of failures that are classified as failures, but that are really non-failures, we have a significant difference here. Basically, we use the 4 evaluators that are common in the literature. That are the accuracy. The accuracy is the total, the true positives and the true negatives. So the true case of failures and non-failures that have been identified, divided by the all elements considered, the true and false positives and the negatives. Then we have the accuracy is important because the error is 1 minus the accuracy. As you can see here, is lower for the error, is lower for the rainforest. And the other parameters, the other evaluators are the recall and the precision, that are considered the true positives in one case divided by the true positives and the false negatives, and in the other case by the true positives and the true negatives. So, as conclusion, this paper contributes for the task of the predictive maintenance. We used some machine learning. We used 2 machine learning approaches. It's important to say that we start from an imbalanced set of data with some errors, some data missing. So it's not a pure data set that we are considering, an optimal data set. We consider the automatic hyperparameter optimization, and we achieved a real-time predictive maintenance model. So since we are in the first studies about this, we consider that it is an interesting start for this work. So thank you very much.
Thank you, Carlos. So now it's time for questions. We have to take the first here.
Thanks for the talk. So I have a question regarding the data set. So is it the data set is balanced or imbalanced? Right? So,
It starts as I referred to you in a relation between for one failure for 28 non-failures.
okay.
Now it seems to start with a balance. The question is, when I select the elements, I don't use all the elements. It's important that I guarantee the balance for the training, because if I select the elements for the train, I will not select all the elements. Okay, so if I select in a relation that is quite imbalanced in one way or another, the model will not be good.
Okay. So like, can you explain like the reasoning behind such a low F1 score with the neural network scheme which you propose? It was 0.27 F1 score. So like, what do you think? What could be the reason of such a low F1 score?
The
For
low
the F1 score.
Mhm.
Yeah.
I think, let me see, is here. Yes, yes. The F1 score is really low in the artificial network, but this is what we obtain, and the main problem are the reduced values in the precision.
Even
Okay.
though random forest is also.
Yes.
So there should be something related to data set, like
Yes.
because
Yes. Maybe this is the problem. If you look to the accuracy is good, but in terms of the precision and in terms of precision is something that is not good in the data set. Yes.
Thank you for your nice presentation. I was wondering if you can elaborate a bit on where the predictive part comes into play. Is it, do you have some prediction horizon that you consider, or is it like early fault detection? And in that case, how early do you actually detect the faults?
Basically, in terms of the manufacturing, what we need is to continuously obtain information about the machines, by the sensors, and to predict when they will have problems, when we'll need, because we need to actuate in terms of maintenance before. This is a continuous process. This means that our models need to be updated from time to time, because the reality can change. So if, for example, if I start to do my work now, and I try to use in January or February, maybe it's okay, but as things may change, maybe this model is not good for from now to 1 year. So I will need to do the training. I don't say continuously, but at least from time to time.
Okay, maybe I can ask another question as well. When you define the objective of the model, are you then considering fault detection? Or are you considering, are we operating in a faulty state right now? Or are you considering another objective? For instance, are we gonna be operating in a faulty state in X amount
In
of
this
time?
case, the goal is to obtain a trend for a failure. Okay, it will not. We try to avoid to detect. Okay, I have a failure now in the machine because the system stops. Maybe the line will stop. What we'll need to consider is, okay, now we are in a situation when we have a trend for a failure. Maybe we'll have 1 month or 2 months or 15 days to solve this problem, and the question is to decide when we will do that. And this is a different problem, because I need to look to what is scheduled to that machine. Maybe I need to take the load of this machine and or of this line and change to another line. Maybe I need to use more time after to recover. It will depend. These are questions that are more related with production engineering processes.
Okay, thank you for your answer.
So we don't have time for any more questions, but feel free to reach out to Carlos in the break. So I would like to thank you, Carlos. So just take this one.